Okay, so we'll in this video and a couple of videos hence from here, we'll look at processes, right? So we've already looked at memory management and how the operating system boots, and every time an OS wants to run an application, it essentially creates a process, right? So we've looked at this slide quite often before, where we define a process, and we call this process as an executing application, or we say a process is essentially a program in execution, right? So we've seen this small C program which essentially prints hello world on the screen. We compile this using a compiler GCC hello.c to get an executable, right, which is essentially a.out. So this executable is an ELF executable. ELF is essentially a format, and this executable is stored on your hard disk, right? To create a process, we run /a.out, where with the help of the operating system, a process is essentially created, right? So the process is an important abstraction of the operating system, and as we've seen before, this process is identified by a unique virtual address space and comprises of the code, data, stack, and heap, right? Now, out of these four things, the code, data, stack, and heap, the code and data are essentially copied from the ELF, right? While the stack and heap are created dynamically, okay? In addition to the code, data, stack, and heap, the operating system also holds some information about the process. Essentially, the operating system would hold the state of the process and also have something known as the kernel stack, right? So notice the difference. So the code, data, stack, and heap are going to be present in the virtual address space for the process. The state of the state of the process and the kernel stack are essentially present in the kernel space, right? The state comprises of registers, list of open files related to processes, and so on. So we'll get into details of what the state essentially means a bit more in detail, right? So just to summarize, what's the difference between a program that is an executable and a process? What we see is that a program executable is essentially just code and static and global data, while a process, in addition to this code and data, also comprises of heap, stack. It comprises of a state of the process, and it comprises of another kernel stack that is present in the kernel, right? So a lot of besides just the code and the data, there are a lot of other entities also present in a process, right? Another thing is that one program can create several processes, right? But a process is unique, a unique isolated entity. Okay, so as we have seen in the previous videos, a process is essentially identified by a virtual address space or a virtual address map, right? So this virtual address map is a contiguous range of addresses starting from 0 to some address called max VA, which is the maximum virtual address, okay? And this in order to create this virtual address space for this particular process, the kernel would need to maintain this hierarchy of page directories and page tables, right? So in the x86 with its three levels of page tables, you would have the L2, L1, and the L0 page tables for each process that it executes, right? So for every process, you'd have this hierarchy of page tables, which would uniquely identify a particular process, okay? Now, uh, now within this virtual address space of a process, it is essentially divided into two parts. One is called the user mode part, or the user space, which is accessed by the user, and the other one is essentially a supervisor mode, accessed by the supervisor mode. Right. So, what is this user mode and supervisor mode? We'll very briefly recollect. Right. So, most processors like the RISC-V have multiple operating modes. Right. So, RISC-V, for instance, has three operating modes: the machine mode, supervisor mode, and the user mode. Right. The supervisor mode essentially comprises of the kernel, like essentially the kernel runs in the supervisor mode. Like most kernels like Linux and x86 run in the supervisor mode. On the other hand, most processes run in the user mode. Right. So, when I run a program, the most of the functionality of that particular program runs in the user mode. The machine mode, on the other hand, is just used for very specific tasks, like for some security related tasks. It's used to run the bootloader. It's used to essentially abstract hardware, and very critical hardware related tasks or security related tasks are done in the machine mode. The reason we have these segregations is to essentially isolate the various isolate between the various execution entities, right. So, if a process is running in the user mode, it will not be able to access any data or any pages that is configured for the supervisor mode. So, in other words, if I run a process, it cannot directly access the code or data that is present in the kernel mode, right, because the kernel mode is essentially configured to for the supervisor, right, while the process runs in the user mode. But also note that the reverse is true, that if you have a program running in the supervisor mode, like for example the operating system kernel, then it can access any memory or any page that is configured for the user mode. Okay. So, coming back to this, right. So, we have a virtual address space for a process and is split into two parts. The supervisor mode part comprises of something known as the trampoline and the trap frame, while everything below that, including the code segment, which is the text and instructions, the data stack and heap, run in the user mode. So, what does this essentially mean? So, this means that if I have a code, or if I have some code over here, so this code could essentially load data from the data segment, or from the stack, or from the heap, right. It can access, it can do anything within this particular range, but it will not be able to access the trampoline or the trap frame, because the trampoline and trap frame are in the supervisor mode, while the heap, stack, data and the text is executing in the user mode, right. So, why do we need this? What is this trampoline and what is the trap frame? We'll get to know a bit more later, but what we need to understand right now is that this trampoline and trap frame is very closely related to the operating system kernel, while the data, stack, heap and the text section are more closely related to the program that is essentially written. Okay. Now, so this is a quick recollection of the virtual address space or the process address space. So, each process that is created or that executes on your system has its own virtual address space. And as we have discussed in the previous videos, to create each virtual address space would require a unique set of page directory and page tables that would create this mapping from the virtual address space to the corresponding physical memory. So, here for instance, I have two processes, and each process would have its own set of page directory and page tables, right. Also notice that each of these processes has this kernel or the supervisor mode part of it, where there is the trampoline and the trap frame, right. So, this trampoline and trap frame is a common entity for any process that executes, right. So, the code and the data that is present in the trampoline is going to be common across all the different processes that execute, right. The user mode part, comprising of data, stack, heap and the code, can differ from one process to another. Okay. So, this is another view of the virtual address space. So, we had the virtual address space for two processes, process A and process B. Each of them is essentially this contiguous region starting from 0 to some very high value, and it is essentially split into blocks of at least typically of 4 kilobytes. Then, with the help of a hierarchy of page tables, these virtual address space is then translated to a address in the physical memory. So, for instance, here is some data or instruction. It gets translated to some location in the physical memory. Now, if I have multiple processes, I can now share my physical memory, and almost transparent to the programmer. This translation is handled by the hardware. So, we will focus now on this on the process stacks, right. So, the process stack is something which we are familiar with, right. So, typically when we create a process, we know that any local variables are stored in the stack of the process, and the stack is also used during function calls to save the return address or to save some critical data such as the stack frame and so on, right. So, the user stack of a process essentially is used when is used for normal for standard operations or standard during the standard execution of the process, comprising of the things like local variables and things like that, right. But from an operating system perspective, along with the user stack, there is also a kernel stack for the process, right. Now, the kernel stack for a process is present in the kernel's address space. Notice the difference, right, that the user stack for the process is present in the process's virtual address space, but the kernel stack for the same process is present in the kernel's virtual address space. So, from the previous videos, recollect that we've shown how the x86 OS creates this kernel virtual address space. Now, what we are saying is that within this kernel's virtual address space, for every process that executes, it creates what we call as a kernel stack, right. So, what is the difference between the two, right. So, when your program is typically executing and you are executing functions within the particular program in the user code, then you use the user space stack, right. On the other hand, when you translate and this particular process invokes a system call or there is an interrupt that gets executed, then the kernel executes and makes use of the kernel's kernel stack of for the process, right. So, this kernel stack is used mostly for when there is a system call or when there is an interrupt that executes, right. So, why do we have two different stacks? Why do we have a user stack for a process and as well as a kernel stack for the process, right. So, the main advantage is the fact that if there is a problem in the process and there is, say, a corruption in the stack of the process, then it does not affect the kernel, right. So, because we have the two stacks which are isolated and totally independent of each other, the kernel stack can function independently of the user stack and does not and cannot be affected by any bug or any other problems that can occur in the user stack of the process, right. So, we obtain isolations, and this can essentially prevent a lot of attacks which may otherwise crash the operating system kernel, right. A popular attack which we will see later on during the course is the buffer overflow attack, right, and your stack would not essentially affect, your kernel stack would not be essentially affected by such buffer overflows. Okay. So, in addition to the kernel stack for the process, the kernel also maintains what we call as the proc data structure for a particular process. So, for every process that executes, in addition to the kernel stack, the kernel also has a unique entry called the proc data structure, right. So, the proc data structure, essentially sometimes called the PCB or the process control block, it's essentially contains keeps track of critical resources used by the process, such as the files that are opened, the amount of memory used by the process, the state of the process, and things like that, right. So, this process control block in XV6 is defined by the structure called struct proc, right, and as mentioned, it holds important process specific information. Okay. So, if to understand or to look at what this struct proc actually looks like, you could essentially go into the look into this file called proc.h in your XV6 source code, in which there is defined the struct proc, right, and the struct proc essentially looks something like this, right. So, each process would have a structure of this particular form, right. So, there are multiple entries that are present. We will go into many of these entries throughout the source of the code. We will keep repeating them. So, currently we look at some of the critical and important entries, but what is important for us is that this struct proc is used to define an array of procs, right, defined by n as follows, right. So, what we are doing is we are defining an n proc. The n proc is essentially some number, like typically 16 or 64 or something like that, which defines the number of proc structures that you want, right. So, in XV6, this essentially defines the maximum number of processes that you can run at a given instant, right. Why is this so? Because each process would uniquely get one of these proc structures, and therefore you can have 64 such proc structures for at any given instant of time. Okay. In more sophisticated operating systems like Linux, this numbers could be there are two things, right. So, it will not be statically defined like this array, but you could dynamically define this kind of a structure. And the second thing is the structure would not be so small as we see over here. There will be a lot more entries present, but still the critical entries are what we essentially see over here. Okay.